for the day of today, I was thinking of what should be presented, whether should we present on the projects which we are doing, or rather as the day itself is there, that is the still day, should we discuss on the still itself. So thinking on so instead of discussing on the projects, I will be discussing on the behavior of the still, and that's what the presentation talks about. So I have chosen the topic of experimentation or experimental behavior of tapered beams. So the presentation contains introduction, numerical simulation, modeling, how what it has done, experimental validation, and findings and discussion. So for any structural engineer, or rather, is a steel structure, is a steel structural member, or it is a gold? If you think on these lines, for a structural engineer or a civil engineer, it will be a structural member. However, for the case of sales engineer or to the customer who the sales engineer is selling to, it will be gold for them. So considering that, always the structural engineer will think of increasing the steel, and the customer or the sales engineer will be thinking of reducing the steel. So if we talk about the PB, rather 15 years back, most of the industry in India was working on conventional structures. So at that time, whatever the customers or consultants were there, this concept was new to them, and they were working with the conventional structures. So conventional structures means what? Whatever the readily available sections were there, rolled form sections were there, or readily available materials were there, that was the part of the industry. So considering that we had a rather consultant or rather structural designer had very minimal options to optimize the structure when using the ready-made available sections, because that was the restrictions with them. However, with the inception of PEB, wherein high yield strength material was being started using on, and second thing, the very sophisticated techniques of welding has been introduced. So all the, what we can say, hot roll sections are being replaced with the plate sections, which were converted by welding the plates in the I sections or required form of sections. So that's how the PEB came into picture, and currently after 15 years, that is in this era, rather what we can say, this is the most popular structural type or design is being used in India, and it's worldwide, right? So again, thinking of PEB, the primary, there are mostly two items, like primary members and secondary items, or secondary members, and rest are the miscellaneous items in the structure. So if you remove all these secondary and what we can say miscellaneous item, because the primary structural members contribute to 40 to 60% in the tonnage, total tonnage of the building. So considering this aspect, because this 40 to 60% is very huge amount, and can we think of optimizing this particular item, that is the primary structural item in the structure? So the hot roll sections, as I discussed, it is we have restrictions to do the optimization on the hot roll sections. So that's how the primary members are being rather used by using the built-up section members. Why it is called as a built-up section members? Because we procure the plates of high-grade steel, which is 345 and above. We cut those plates and make it I section using the automatic welding techniques. So again, right now we have some restrictions with respect to the code and what we can say the equations which are given in the code. So currently in India, rather, we are using the IS code and the American code. And in both the codes has given certain equations, and we cannot go beyond those equations. So in doing so, are we using the sections to its fullest capacity? So this is one of the biggest question right now we have. If you are using the high-grade steel with a sophisticated welding techniques, so we should think of, are we using the sections to its fullest capacity using the codal provisions? So this is one question which comes into mind while discussing on this presentation. So this is the one question, and second question we'll be seeing in the next slide. So before coming to the second question, the biggest enemy of the I section, rather, because I section is the first or very important primary member in the steel itself, in the frame itself. So the biggest enemy of the member or I section is the lateral torsional buckling. So lateral torsional buckling is what? As the sketch shows, there is a vertical displacement of the member, there is a horizontal displacement of the member, and there is a rotational displacement of the member. So I section has its natural property to give its resistance by using its torsional stiffness of the section. However, but that stiffness is very, it is a very lower side, and we cannot use it each time. So what are the factors that affects the lateral torsional buckling? It's the cross-sectional properties, then the material properties, then the length of the beam, then the support conditions for which that beam is been subjected to, then the initial geometric imperfections. So what is this initial geometric imperfections? When we manufacture the beam, it is welded along the length of the beam. So it has a very high heat generation, and in this heat generation, when it gets cooled down, it has certain what we can say localized stresses in that, and due to that, the member undergoes some deflections or gives some camber or in the horizontal and vertical directions. So this is the initial geometric perfection, and also the type of load of application on this beam itself. So the second question which we should ask for, are those only factors that affect the strength of the section? That is the another question, whether does any other factor affect the strength, or that is not been accounted for while designing the sections. So currently, while reviewing the IS code, where the design strength of the beam generally is given by that equation, which is beta B, ZP, and FBD. So this is the generic equation, and code gives some reductions, or code applies some reduction in order to take care of those initial imperfections, whatever the load applications are there, and what are the factors I have discussed before this slide. So coming to the next slide, any beam's bending capacity depends on its torsional resistance and warping resistance, and the elastic, and it is depending on the, further it depends on the elastic formula which is seen on this slide. So while discussing, or rather while comparing the various codes, that is IS code and AIC code, we can see that in between the IS code and the AIC code, we will see that the AIC code gives optimized results. So that means the IS code gives over design as compared to the AIC code. So you can see the values, wherever the MD values in this particular slide. So what are the applications of this web tapered beams? Just to highlight of those in what PB Industries follows is, this is a typical pre-engineer buildings, and the tapered beams what we were discussing about is been seen on the screen. So when asking those questions, it was decided that what would be the objectives to solve those answers of those particular two questions. So objectives were to investigate the effect of web tapering, okay, web tapered eye sections on the buckling analysis using the finite element analysis, and validating that finite element analysis by experimentation, so real-time experimentation. So second objective was to see what would be the geometric imperfection or initial geometric imperfection effect on the tapered eye sections, or what we can say the capacity of the eye sections, and that is done by using also the finite element analysis. So to investigate the effect of profile type of the section on the buckling analysis, there were three types of profiles chosen while doing the analysis: the profile type 1, profile type 2, and profile type 3. So these were the objectives which were framed while discussing those questions in mind. So what methodology was used was, so the sections were selected as seen on the screen, and the sections were selected such that can be tested at the testing facility. So while doing the finite element analysis, ANSYS software was been used. The material parameters like Young's modulus and Poisson's ratios as displayed on the screen has been considered, and true stress strain data for isometric used analysis, isometric material is used for the nonlinear analysis. So this is the graph of that particular data. So in order to do the finite element analysis, there is a need to ingress the, what we can say, geometric imperfection in the model itself. So for doing so, we have to do the buckling analysis of that particular beam. And after doing the buckling analysis, there will be first mode, what we can say, deflection. And that first mode deflection, we have to, what we can say, get into the nonlinear analysis model with some, what we can say, magnification factor. So that magnification factor is, if suppose L is the length of the beam, that divided by 1000 is been multiplied with the buckling values. That's how the nonlinear analysis geometric imperfection is been taken care. So shell 181 element is been used for this particular analysis, which has which is suitable for large rotation cases, for large nonlinear applications, and the performance of nonlinear buckling finite element analysis convergence was tested, and it was found that 25 mm plate, or what we can say, element was suitable for using this analysis, doing this analysis. So for doing the nonlinear or solving the nonlinear problem, Newton-Raphson's iterative method was being used, and some 2-3 points was mentioned rather to explain what is that Newton's Raphson iterative method is. So boundary conditions while doing the testing and whether doing the analysis where it was pin supported at both the ends, load was applied. So point load was applied at the center of the beam. The displacement control analysis was done. This is an interesting fact because why displacement control analysis? Displacement control analysis means what? A beam is there. We apply a displacement on that at the required location of the beam. The beam will get undergoes displacement, and it will fail. That whatever the displacement is been applied, we know the reactions, and we compare we graph the reactions versus the load. So this particular analysis is done in the finite element analysis, because if we go with the load application, what happens after the, what we can say, the failure, the load convergence failure, after the failure of this beam, the further load application won't happen, and we will not get the further analysis of that particular beam. So that's the reason we are using the displacement control analysis. So for, in this case, while doing the experimentation, the length of 1.835 meter was being used, and the center to center span where the beam was placed, it was 50 mm from each end, that is 1.735 was the center to center span of the BT, what we can say, support. Various taper ratios were being used, like from, say, from example, 0, 0.75, 1.5 and 3 was the taper ratio used. The results were compared with the IS code and AIC code. So experimentation result, finite element analysis results were compared with the IS code and the AIC code. So to do the experimental validation, these were the beams which was manufactured in Everest. So Everest has sponsored this experimentation work, and these were tested in one of the premium institutes of India, and the various sizes which was used, rather the 3 profile types as I discussed, profile type 1, profile type 2, and profile type 3. These profile types with various taper ratios were been fabricated and tested at one of the IITs of India. So while manufacturing or fabricating these beams, steel plates were being used, which were welded to form the built-up sections. The grade of the built-up was, or plates was G345, which is equivalent to 2062 code of the India IS. And the supplier of the plate was actually, it was a Tata. The plates were brought from the Tata Steel, and those plates were being used for the fabrication. So while for doing the welding, we have done the submerged arch welding, which is seen on the screen. So the thickness of the flange for this particular beam was 6 mm used, and 5 mm was the web thickness used for this fabrication, and the weld thickness was 3 mm used for manufacturing of this beam. So this is a fabricated beam, rather this is one of the beam which during the fabrication of the picture was taken care. So this is the actual testing which we have done on that particular beam, and this particular machine can test 600 tons of load. This machine can apply the 600 tons of load on the particular section. So this is another view of the testing, and this is what has happened with one of the beams which we have, what we can say, manufactured. So as we said, these are the three types, profile types we have discussed, and these three sections, above that sections, this is the finite element, what we can say, section been shown on the screen. So we can see the results in displayed on the screen, where you will see that the profile type 1, the profile type 2, and the profile type 3, we can see that in all the cases, whatever the codal equations or whatever the code specifies the limits of the structural member, against of that, the finite element analysis results and the experimental analysis results gives a very, what we can say, good value. So there is still a margin of where we can see that, or where we can think of whether can that margin can be utilized for the designs. So against of this, also we can see that the experimentation values are very well validated with the finite element values. As you can see the graphs, the top two graphs are experimentation versus finite element analysis values, and these are within the range of 95 to 96%. So that's how the validation has happened, and the code AIC values are seen in the blue, what we can say, graph, and IS code has two options. You can design the IS code, we can apply the equations as per the 8.2 clause or appendix E clause. So using those clause, we see that the IS code is a very old design. Rather, we can say that it is the most design of optimized design is given by AIC code versus the IS code. And now the first question's answer is yes. Can we think of this margin? Whether can we think of something modification in those equations so that this particular material can be used to the fullest capacity? So that is the first question which we get an answer over here. There is some reserve strength, and we should think of this reserve strength, and we should study further on this particular aspect of capacity. So the second finding what we have seen is, just last slide. The second finding what we have seen is, the second question is there any another important parameter that is missing? Yes, there is some another important parameter that is missing is the profile types. So the profile type 3, you can see that for the profile type 3 gives the best results as compared to the profile type 2. And the profile type 2 is not desirable. That is what we can see from the graphs itself. So that's how this particular aspect is not taken in any of the codes. And this is the another finding which you have seen while doing this testing and finite element analysis. So this is the second, what we can say, the question's answer. Yes, there is certainly the type of profile that decides the capacity of that particular member. So if we discuss, the profile type 2 shows strength reduction with increased taper ratio, and hence it is not recommended for the use. The basic reason is the load, when we apply towards the top of that particular member, that load is towards the destabilizing part of that member, and that's the reason the strength goes on reducing as the tapering ratio increases. The type 1 and the type 3 is having a close results, and it is between 10 to 15% the results are varying. So 2 and 3 profile can be used, and the best of those profile is profile type 3. So that's what these findings are being seen while doing this entire experimentation and finite element validation. So thank you for